All right, let's talk about the secret language that engineers use to, well, build everything. From the tiniest little machine to the most gigantic skyscraper, it all comes down to understanding forces. And to do that, you've got to speak the language of vectors.
I mean, seriously, have you ever stopped and just looked at one of these things? How does it lift literally tons of material without just folding in on itself? It seems simple, but really it's this incredibly complex dance of invisible pushes and pulls all happening at the exact same time.
And that's precisely what vector analysis is. It's a language that was invented to describe, to calculate, and to ultimately control all of those invisible forces. So let's jump in and learn the basics of this really powerful language.
Okay, first things first, we have to understand the two most basic words in this entire language. See, in mechanics, every single physical thing we measure is one of two types.
On one side, you have scalars. These are the easy ones. They only have a magnitude, a size. Think about something like mass or volume. A 10-kilogram weight is just 10 kilograms. End of story. But on the other side, you have vectors. And a vector needs two things. It needs magnitude and it needs direction. A force, a push, or a pull isn't just about how hard you're pushing. It's about which way you're pushing. And that direction is absolutely crucial.
This is exactly why we use an arrow to represent a vector. It's the perfect visual, right? The length of that arrow tells you its magnitude, how strong the force is. And the direction it's pointing, well, that tells you its direction. It's simple, it's elegant, and it is unbelievably powerful.
So what happens when you've got more than one force acting on an object? Well, you have to add them up. And the best way to get your head around vector addition is to think about it just like following a map. Let's just use this analogy for a second. Every part of that instruction is a vector. 10 steps is the magnitude, north is the direction. Then you have the next vector, 5 steps, east. Each instruction just builds on the last one. So after you've walked north and then east, you're obviously not where you started. So what's the single, straight line path to get from your starting point to your finish line? What's the shortcut? In engineering, finding that single path is called finding the resultant vector.
So how do we find that resultant? Graphically, we use a really simple method called the triangle rule. It works just like this. First, you draw your first vector. We'll call it A. That's your walk north. Then, right from the tip of that first arrow, you draw your second vector, B, connecting them head to tail. That's your walk east. The resultant, R, is simply the one arrow that connects where you started to where you ended. That's it. It represents the combined effect of both of those separate moves. Now, drawing arrows on a piece of paper is great for a 2D problem like our map. But what about that crane? Forces are pulling up, down, sideways in all 3 dimensions. Trying to draw that out accurately would be an absolute nightmare. We need something way more precise.
And that's where we get our big upgrade. We're moving from a simple paper map to a high-precision 3-dimensional GPS. This is the real power of what we call Cartesian vectors.
Think about it. Instead of vague directions like north and east, a real GPS gives you exact coordinates on a universal grid. And that is exactly what engineers do with forces when they're working in 3D.
So here's the breakdown. First, you set up a 3D grid with 3 axes at right angles to each other, X, Y, and Z. Now, you can take any force, no matter which way it's pointing, and break it down. You just ask, how much of his force is pushing along the X-axis, how much along the Y, and how much along the Z? Those are its rectangular components. And to keep track of it all, we use these little markers called unit vectors. I points along the X-axis, J along the Y, and K along the Z. They're like the universal signposts for our grid. So, when you put it all together, any force F can be written out just like this. This equation is basically the vector's GPS coordinates. It tells you with perfect precision how much push you have in each of the 3 directions. No guesswork, no messy drawings, just the facts. And what if you want to know the total strength of that force, the actual length of that original arrow? Well, for any vector A, we've got this formula. And if it looks familiar, it should. It's basically the Pythagorean theorem, just beefed up for 3 dimensions. It lets us calculate the overall magnitude from those individual X, Y, and Z components. Okay, so our vector GPS is fantastic for describing a single force. But what if we need to know how 2 different forces are interacting with each other? For that, engineers have a very special tool in their toolbox. It's called the dot product. Now, don't get hung up on the formula.
The big idea is that when you dot two vectors together, you get back a single number, a scalar. And that number tells you how aligned those two vectors are. If they're pointing in the same direction, you get a big result. If they're at a 90-degree angle to each other, you get 0. It's a measure of their agreement, so to speak.
So what do we use this tool for? Two main things. First, it is the perfect angle finder. You can use it to calculate the exact angle between any two forces. And second, it lets you find the projection of one vector onto another. This is huge. This answers the question, if I'm pulling in this direction, how much of my effort is actually helping to move something along that specific line? It's incredibly useful.
All right, so we have our basic language, we have our GPS system, and we have our angle finder tool. Let's put it all together and bring it back to the real world.
And it matters a whole lot. Because without this system, designing anything complex and, more importantly, safe would just be pure guesswork. Every single calculation that goes into a bridge or an airplane or a skyscraper relies on understanding and managing these force vectors with absolute precision. Just look around you. The reason a bridge truss is so strong is because of balanced force vectors. The way a robotic arm can move with such amazing precision, vector calculations. The crane we started with, it can support those huge loads because engineers analyzed every single vector acting on it. From aerospace frames to transmission towers standing up to the wind, it's all built on this invisible language. When it comes right down to it, that's what vectors do. They take a simple idea, like a push or a pull, and they turn it into a precise mathematical blueprint that lets us build a safer, stronger world. So I'll leave you with this thought. The next time you cross a bridge, or you're just looking up at a skyscraper, take a second. Try to imagine that invisible web of vectors, all of those arrows pushing and pulling, all in perfect balance, holding the whole thing together. That's the secret language of engineering. And now, you know how to speak it.